Hello, everyone. So today we're going to shift the focus to the transaction. It's one of my favorite topics. It's something that I've personally been focused on in terms of research for the past 10 years as well. And I would say transactions are at the core, sort of core topic of database research, to some extent, even distributed system as well too, and even blockchain. The notion of blockchain is, one could argue, is nothing but transaction, and in particular, a secure kind of transaction. So it's a core topic, and it's exciting. So, and the remainder of this month, the focus is really going to be on transaction, and the third milestone focus will be entirely on transaction as well. In the second milestone, as we talk about the merge, then we have to deal with concurrency issue, which those concurrency and synchronization also has an important role in transaction. But the really that feature of formally supporting it, it's only going to show up in the third milestone. So what is a transaction? Is, as we had mentioned in the first session, is that if you talk about digital form of contract, is that the reason we have multiple parties trying to perhaps buy or sell something, essentially they are engaging in a form of a contract. And a transaction is a digital implementation or a digital encoding of that contract. Basically says person X pays certain amount of money to person Y, and on behalf of that money exchange, for example, a book gets shipped. So that set of action is conceptualized as a contract, and that contract is formulated as transaction. And when we talk about transaction, we need to be able to talk about this type of contract, and we need to talk about the property that makes this contract correct, or the execution of that is correct. So therefore, transaction have set of properties that allows to assess the correctness of it and understand the semantics of it. The other important property of transaction is that if we have formalized a notion and the semantic of what it means to execute one transaction correctly, then in order to be able to build system that can scale, potentially we want to be able to execute multiple transactions at the same time. So then we need this notion of concurrent execution. And the notion of concurrent execution is what really makes transaction, in fact, interesting. Because if we are doing a single transaction at a time, sure, we need to talk about the semantics of what that means to be correct. But it's a much simpler environment because just one thing happened at once. So one of the key property of transaction is that you want to make sure, for example, to be atomic, meaning either the payment from person X to person Y received and the book is shipped, or none of those two actions take place. You don't want to be in a situation that the money is paid, book is not shipped, or the book is shipped and money is not paid. So that notion of the atomicity, meaning that all the terms of the transaction must be executed, that all or nothing is as sort of that centerpiece of transaction processing. So, and we often talk about those property as asset. A stands for atomicity, C stands for consistency, and the consistency here means that if the database was in a consistent state, after the execution of the transaction must remain in consistent state. And as we had talked before, consistency here means in terms of the integrity constraint. So if we define a set of integrity constraint that must be fulfilled, so they must be fulfilled at all time, before the execution of the transaction and after the execution of the transaction. So the database always transition from one consistent state to another consistent state. An example of these integrity rules or these constraints, or for example, is your balance has to be greater than 0. We cannot have negative balance. You cannot pay someone the money that you don't have, or you cannot sell more seat in the airplane than that you have, because people cannot stand on the aisle. So if you have 100 seats, you can only sell 100 to 200 customers. So those are the integrity constraint that must be satisfied. And then the finally, or not finally, the fourth property is the D, the durability. And that's something we're really going to focus on in the second assignment that we've already talked about. It is that how do we persist the data on disk? And in fact, the sort of the mindset of the database is that the data resides on disk, and then whenever we need a piece of information, we bring it into main memory, into our buffer pool, and when we're done with it, we write it back to disk. And that's that flow of the data residing on disk brought to memory on demand and writing it back to disk. It's what provides that durability. Of course, the notion of logging is also crucial in order to ensure durability when crashes occurs. So that's the durability aspect. So first milestone, we assumed everything is in memory. So really, we don't really have notion of durability. In the second milestone, we say, okay, the data is on disk, brought to memory. So the notion of durability gets satisfied. Currently, we're assuming we're doing one operation at a time. So since it's a single operation, so by definition is atomic, either that operation goes through or not. We're not dealing with executing multiple operation in the context of transaction. So that's something that will come into the third assignment or third milestone. And also, since we're doing things serially, things are much simpler in the first milestone. So now the third thing, so we said acid is A is the atomic, C is consistency, D is durability, and then the third one is the isolation. And isolation is really at the heart of this concurrent execution. And isolation means I should be able to allow concurrent execution, but from the purpose or from the perspective of each transaction, I should run in isolation, meaning that the net effect of other ongoing transaction or the action of the other concurrent or ongoing transaction should not interfere. So when I have a strong isolation, it means I am able to run multiple things in parallel, multiple things concurrently, but they will not interfere with one another. So for example, if I'm writing something, another transaction is not going to override what I was working on. Or if I'm reading something, another transaction is not going to, again, override what I was reading. So all of those unwanted interference, or actually any interference among would be unwanted. So all of those are eliminated. And that now becomes the notion of how do we define correctness in a form of concurrent execution. So the basic of criteria of the correctness of transaction is one atomic, one is to make sure it's durable, one make sure it's consistent. And so those are the properties that depends on sort of, you can say, more on the semantic of what is being executed. The isolation is really on the operation, how things are actually getting executed, and to make sure that the execution is correct. What is being executed, we know. We need to make sure the data is consistent after it's executed. What's being executed, we know it has to be atomic, has to be all or nothing, and it has to be also durable, meaning something that was executed needs to be remembered forever. So those are sort of more direct property of the transaction. All or nothing, consistent, remembered forever. So those are atomic, consistent, durability. Isolation is not really necessarily the direct property of a particular transaction. Isolation is an operational semantics in a sense, or executional semantics, meaning that transaction itself, they don't really care about isolation because they assume they're running independently. But it's isolation becomes really a property of the database that allows providing concurrent execution, but ensuring those concurrent execution do not interfere with one another. So I'm going to pause here and see if you have any question. Okay, so one more time, acid is atomic, all or nothing. That's a direct property of that contract. I want my contract to be all or nothing. Consistency, I want to make sure that contract does not violate the rules of the game, or the rules of the rules of the game, meaning that I cannot give somebody a money that I don't have. So that's consistency. So all or nothing, consistency, and durability, meaning that if I'm transacting with someone, if I'm writing a contract and executing a contract with another party or multiple party, I want the ability to remember that contract forever. And that's durability, the ability to be able to remember that. So those are the direct property around the actual transaction, around that contract itself. That final property, isolation, is about, I want to be able to, as a system view, from the system perspective, I want to be able to execute multiple transactions at once. And I want to make sure those three properties that I indicated earlier satisfy. Also, I want to make sure that the concurrent execution does not create interference, does not create conflict, and does not create anomalies as a result of that things are running in parallel or things are running concurrently. And why we want to do concurrent execution? Well, again, these are some of the topics I've already touched upon earlier, is that, well, hardware is changing. Before, I may have like a single threaded hardware, or I may have like 2 CPUs. Now I could get a machine with hundreds of cores. And if I don't do things concurrently, basically that machine is going to be idle. And also, as we talked about, is that if the data is residing on disk, and I know the disk is much, much slower than my main memory, then the time that I'm issuing to bring the data from disk to memory, then this is a time that I not want to sit idle. I want to be able to do useful tasks. Or is that if I'm a transaction, I read a bunch of data items, then I need to kind of run a very elaborative financial model or a machine learning or a deep learning or whatever it is that I want to run. During the time that I'm doing all those execution, I don't want to stop the whole database. I want the other transaction to go through, as long as I can guarantee that isolation, as long as I can guarantee that those concurrent transaction is not going to interfering with the action that I'm doing. So again, it's crucial to be able to support concurrent execution and the ability to be able to interleave the actions of different transactions. And again, from the database, as I mentioned, is that really the database cares about the data is read and the data is written. What is computed, or how the user decide the outcome of what to be written based on what is read, database is kind of oblivious to it, doesn't really care. At the end of the day, it sees something is being read and something is being written. And as long as it can provide correctness at that level, well, that's what it's important. And again, transaction is that abstract view of the user program. That transaction is basically a contract, and with that abstract view, you can think of a transaction as just simply a sequence of read and writes. And sure, you may do some complex analysis based on what is read to determine what is written. But from the perspective of the database, transaction is nothing but a sequence of reads. Bunch of records are read, bunch of records are written. It's possible that I only read a record, I don't need to write anything, and vice versa. It's possible I don't read anything and I just write something. For example, I just said, well, every account just gets $5. I don't really maybe even don't need to read anything. I can just add $5, or I could just say everybody's salary should be now 5,000, and I don't really need to even know what the original salary was. I can just blindly go and write those values. So there are cases that what it's called as you do blind writes. You write things without even reading anything. But again, it comes down to basic actions of read and writes. And if you've noticed in our assignment or in milestones, we're really just focusing on those read and writes. We're really focusing on those fundamental operations that the database needs to provide. In the last few lectures, we're going to talk about sort of more elaborated things that can be done. But at the fundamental level, or the most basic primitive level, is just reading and writing records. And that's also the basic primitive on which transactions are operated as well too. Any question? So again, from the user perspective, they're not concerned about concurrency. They're not even beneficial. I mean, for the user, it's just submitting a transaction. They want to make sure it's atomic. They want to make sure it doesn't create inconsistency, and they want to make sure it's durable. So this notion of isolation, it's kind of, again, it's a property of the database. And one you can say is that, how do I now talk about, so I know what atomicity means. It's very easy to understand because I say either everything gets executed or nothing gets executed. Consistency, also very easy, is that if I have set of rules about my data, then those rules always need to be satisfied. Again, really easy to reason about, really easy to understand. Durability, also very simple, is that any changes made to the database or any new information added to the database, they must remain forever. Again, very simple property. But what does it mean for a concurrent execution to be correct? That doesn't seem to be as simple. So can you think of a way of how are we going to formalize what it means for concurrent execution to be correct? And what concurrent execution really means is that you interleaves the actions of various transactions together. So maybe I do a couple of writes and reads from one transaction, and then I end up doing read and writes for another transaction, then another transaction, then I come back to the first one. So there is some interleaving of actions of different transactions, either by the same thread or different thread, doesn't really matter, but it's the order in which things are executed are kind of no longer follow that serial order. So how can you think of a way that we formalize the correctness of a concurrent transaction in a very simple way that we were able to formalize the correctness of atomicity, the correctness of consistency, and the correctness of durability?
I think I remember reading that if there exists some serial order of transactions, if we somehow are able to interleave all of these other transactions to become that serial order, then we can consider it concurrent.
Yeah, so that's you're definitely on the right track. But why is it a serial? What's special about serial execution? Why is that why is that important?
I guess that has to do with the integrity. Like one transaction can't mess up the, like a transaction that was supposed to come before it or after.
Exactly. So again, remember we said if there was no concurrent execution, then we already know atomicity, we know durability, and we know consistency. It's only when I try to do things concurrently, it's the only time that it's possible that the action of one transaction may conflict or interfere with another transaction. So then, if there's no concurrent execution, then isolation is trivially satisfied, because if I'm doing things one at a time, basically by default or trivially, things are isolated because nothing is happening at the same time. Only one action is happening at the same time. So the isolation is as satisfied. So now the insight here is that if I can execute transaction concurrently, but then I can show the net effect of that execution is equivalent as if I were to execute transactions serially in some order, then I can say my transaction is correct, that execution is correct. Or in particular, that schedule is correct. And the schedule really means that the interleaving read and writes is that schedule means I first executed this action, then I did this action, and did that. So it's basically the order in which things were completed. So that becomes the core aspect. So again, we talked about it. Each transaction leaves the database in consistent state. Integrity constraint must be satisfied. And the issue is really about this interleaving of the transaction. And moreover, is we need to ensure isolation, that they don't cause conflicts, but also we need to think about what happens if thing crashes. So even if you are very careful to make sure the action of one transaction does not interfere with another transaction, but if you're in the middle of the execution and perhaps some of the effect of transaction are persisted to disk and maybe some of them haven't, then once the system crashes and the memory is gone, then how do we ensure what the data that remains on disk is still correct and is still consistent, or it can brought to a consistent state? So that's the notion of crashes. And we really deal with crashes. It's part of the recovery, and the recovery really relies on logging. And we kind of touch upon it for this the end of this lecture as well. So again, atomicity, as we mentioned, the transaction is all or nothing, and the transaction fate is either a commit, meaning all the changes of transaction were sort of accepted by the database, therefore they need to be remembered, or abort, meaning that either one or all of the transaction action were not successful, thereby nothing, there should be no net effect of the transaction. Any change in the transaction is done. If it's aborted, must be forgotten and must be eliminated forever. So we shouldn't have any, none of the side effects of the transaction should remain. And again, so this atomicity, it's crucial, as we have already referred to it. And wanting to deal with those crashes is that if I am taking a log, just conceptually, if every action I do a bookkeeping of it by just simply taking a log of it, then, and I know that my log is always persisted to disk before I actually do any action, I first write it to the log, then I actually go ahead and do that action. Then if something goes wrong and the database crashes, I can always go look at my log and see all the step that was done, and I can bring the database back to a correct state. For example, I can undo any action that wasn't supposed to be done, or I could potentially also redo some action that should have been reflected, but they've kind of lost. So log is basically everything that I do. I kind of on a side, I write down everything that I do. I write to disk everything that I do. And this log will help me to recover my data. And in terms of metaphorically, log, it actually looks very similar in a sense to this append-only data structure that we also have in LSTOR, is that I'm not really changing the data itself. I'm not changing really the base pages. I kind of keep append only of all the things that needs to be, all the changes that needs to go, that needs to be applied to that original data. So this append only notion of just recording things, in a sense, it really has the flavor of a log. In fact, it could be even be a way of replacing a log. So that's sort of an interesting thread of thought on its own as well too. So, but log is essentially an append-only bookkeeping of all the actions that are being applied to the data. So now, kind of let's look at these concurrent actions. So what are these concurrent actions and where could things go wrong? And then we can talk about more formally with regards to that serial scheduled and that correctness property. So these are two transactions, and this is sort of the syntax that we will use: T1, transaction 1, T2, transaction 2. And a transaction usually, depending on the vendor, but normally there is also, there is a kind of macro, or there is a keyword of begin, which indicates the start of a transaction, and also something that indicates the end of the transaction. So transaction T1 begins and ends, transaction 2 begins and ends. And then what transaction 1 does, basically from B account, $100 is transferred to A, and transaction 2 basically just adds 6%, let's say, interest to both A and B accounts. So two simple transactions. One is a transfer of money from B to A. The other one is just basically give 6% interest. Two simple transactions. And when you submit this transaction to the database, you can't really specify which transaction should run before which. So we don't really have that ability. Sure, if both transactions are being issued by the same person, then I can decide, first I'm going to send T1, and once I get an acknowledgement that T1 is successful, then I can send T2. But if these transactions are being issued by different parties, well, then the user cannot say, well, I'm submitting this transaction and you got to make sure this transaction gets executed before anybody else. And that usually is not such a functionality, although possible, it's not provided by any database. So as transactions are submitted to the database have the liberty to reorder this transaction in any way that it wants. And as long as it ensures the net effect of that execution of those transactions were identical or equivalent as if those transactions were executed serially, meaning either T1 or T2 or T2 after T1 or T2 followed by T1, as long as the net effect of executing these transactions, it looks like that if I did T1 T2 or T2 T1, then the database did its job correctly. But it doesn't provide the ability to enforce which order needs to be taken, as long as one of those serial order. So there are two possible serial order again: T1 followed by T2 or T2 followed by T1. And both of them are valid, and both of them will be serial. Any of those to the database provides or executes, it's correct. And if it executes some interleaving actions of T1 and T2 that corresponds or be equivalent as if it had executed T1 followed by T2 or T2 followed by T1, that's also again correct. So if I execute any of them in any serial order is correct. if it concurrently executed and it can be mapped to either T1 followed by T2 or T2 followed by T1, again, it's correct. So now let's see example of how could that interleaving will look like, and that interleaving is what is considered as a schedule. So this is one scheduled, is that first I execute adding $100 to A, then give 6% interest to A, then dock $100 from B, and then give B 6%. So on a timeline, first this action getting executed, then this action is getting executed, then this action gets executed, and finally this 6% interest for B gets executed. So now we are interleaving these schedules. So it's no longer the case that T1 is strictly followed by T2 or vice versa. So this is one interleaving. And now the question is this a correct interleaving? How do we reason about this, whether this is correct or not? Does it look like correct to you? Do you see any anomalies? And oftentimes when we talk about correctness, we say, did it interfere? Did it cause any anomalies? Did it cause something, again, did it cause an anomaly that wouldn't have been there if we had executed them serially? So is it the case here? Do we see any side effect of such an interleaving of a scheduled?
No.
Why not?
Since A is only affecting an A, so even if you run T1, T2 for A first, it should be okay because they're not related to each other, I guess, or correlating to one another.
I'm thinking that maybe it might not be, just because the interest is computed at a different point, so maybe one of the accounts doesn't garner as much interest in their account that they should, but I'm not sure.
So both of you, I think, kind of touched upon an important element. So we're kind of doing actions on A's, and then we're kind of doing actions on B's. But interestingly, so that becomes important property here. We're all doing actions on A, and then we're all doing actions on B. Interestingly, both transactions are touching A and B. So in fact, transaction A and B, they do kind of have a conflict. They have a potential conflict because they're touching the same amount, same data. So we have to be careful in the way we orchestrate this. But what is unique about this, the way this is scheduled right now? What's unique about this interleaving? There's another property in this interleaving, very simple property. What is that pattern that we have here?
Plus first, multiply later.
That's sure, but that's kind of, that's the order. So we're not going to change, we cannot change the order of these. I mean, sometimes technically we're not supposed to change the order of the statement of the transaction. Sometimes we could kind of do some
so
analysis.
T1's things are always before T2's things.
Exactly. So that's important, is that although I am interleaving transaction, but I'm always executing action of T1 followed by T2. I'm always executing action of T1 followed by T2. So in a sense, in this simple example, this will be equivalent to what serial schedule this will be equivalent to.
It's equivalent to just running T1 first and then T2.
Exactly. So as long as I have a schedule and I can show that is equivalent to some serial schedule, we're not saying which one, could be T1 followed by T2 or vice versa. And again, we could have hundreds of different transactions happening. It doesn't, you're not going to be limited to two. As long as we can show that this schedule can be mapped to some serial schedule, we don't care which one, as long as it can be mapped to some serial schedule, And since we know serial scheduled are correct as far as concurrency, because they trivially satisfy any concurrent isolation and concurrency because they're running only one thing at a time, then I can ensure and be sure that my execution in terms of concurrent execution is correct because it looks like a serial schedule. I did it concurrently, but it has the exact same net effect. It has the exact same behavior as if I had done things serially. And I know doing things serially is correct. So if I did things concurrently and I can show it was identical as if I had done it serially, then that's what I wanted to accomplish, and that's accomplished. Does that start to kind of make becomes a little bit more intuitive of this very basic concept of transaction? The entire transactional theory relies on this really basic concept, is that I know serial execution is correct. And if I don't do a serial execution, I do a concurrent execution, but I can show my concurrent execution can be mapped or it can behave the same way as some serial execution, then I can say my execution was correct. My concurrent execution was correct.
How is this interleaving any better than serial operation because the time is still the same?
Yes, that's a very good question. The time is the same, although. So this is kind of one interleaving, but then it is also possible. It is also possible. For example, so now we're talking about interleaving operations, but you could imagine that I had one thread that does these two actions, and I had one thread at the same time doing these two actions. And that would still be correct. And I could do things. So that's another interesting point. Here, we're not talking about, so there is a distinction between concurrency and parallelism. Concurrency says that if I do things concurrently, maybe do some of this and some of that, if I'm doing execution concurrently, can I ensure that the outcome is correct or not? Parallel means I'm doing it concurrently, but I'm actually physically doing it at the same time too. So concurrent doesn't necessarily mean parallel, but a parallel execution is always concurrent because things are happening concurrently. So here we talk about the correctness of doing things concurrently. So now if they can also be done physically at the same time, since I can now reason about its correctness from concurrent standpoint, then I can also, well, that reasoning will be extended to that parallel execution. Again, but we're not really talking about, so that's one way of doing it, but we're not really talking about how are they actually being done. Were they done being by one thread, two threads? What is the mapping of this to thread? This is really just talks about if I were to interleave operations, can I still get the correct result? Now, the next question, which is important, is that how do I do this concurrent execution actually in parallel using multiple CPUs or multiple threads, multiple cores that actually gave me performance benefit? Because if I'm just doing things, interleave things, then maybe I'm not going to get a whole, maybe I don't get a lot benefit. So that's another thing as well. But also, if you remember, I could do, so this example is a bit limited, but for example, if T1 did some action on A, and then we did some action on T2, again on A, but then T1 wanted to do something on C, which T2 is not interested. It's tried to do the action on C, but then C is not available. So while they wait to get the C, now we can go back to T1, add the balance of $100, come back to T2, and now maybe the C is available. I can do the action on C, then I can add 6% to B. So again, you can think of, even with single-threaded execution, the concurrent execution will reduce the wait time. If a transaction wants to do an action, read some data item that is not available right now, it issues the read request from disk, switches to another transaction, and perhaps that transaction, the data that needs to access is already in main memory, so it can do it quickly. But if that transaction is not available, I can jump to another transaction, pick up a transaction that I can do it right away, right now. And so that concurrent execution then allows me to, even with a single threaded, even if I have only a single thread, the concurrent execution could be beneficial. While I send the stuff to disk, while I'm waiting for disk to come back with the data that I want, I can grab something else to do. And when the disk results come back, then I can kind of go back to what I was working on. So again, that interleaving allows me to improve the concurrency. You can think of the interleaving as the time that you need to wait for the disk to spin. During that time, the disk spin to find the right information, multiple things can happen. Of course, the transaction that's waiting for that spin is stuck, but other things can be interleaved and be executed. So two things. One thing is, is the interleaving itself is correct? Can I parallelize that interleaving? Or maybe some action that I invoke, it's take a long time, so I can start another action while that thing is happening in the background. So there are multiple ways that we get performance benefit as a result of this interleaving. Does that make sense? Okay, so how about this interleaving? So this is another interleaving. Again, here, right now, our focus is really about the interleaving. Is the interleaving produce correct results? Now, the question of, can I do things in parallel, or whether this particular interleaving is also beneficial in terms of performance, that's a different question. Here, we're talking about the correctness or the semantics of the way we can ensure correctness of interleaving of execution. So that's first step. Now, if I know how to interleave transaction, now can I make sure that that interleaving can be implemented more efficiently, or that interleaving can be done parallelized efficiently? So that's the second question. The first question is the interleaving even correct to begin with? Because if it's not correct, then whether I do a serial or parallel, doesn't matter, it's all going to be incorrect. So how about this? What's happening here? Is this also, so this is a schedule because something happened in a timeline. Is this a correct schedule?
No.
Okay, why not?
Just if you run T1 first, then T2, versus if you did the interleaving, the result will be different, I guess, in that sense.
So, for example, I mean, yeah, you're absolutely right. A couple of things is that, for one, we first add $100, then give 6% interest. Here, we first give 6% interest and deduct $100. So there is no potential serial execution. Strange behavior. And the reason for that is that T1 and T2 are sort of conflicting transaction because they're hitting the same data item. Something is conflicting if the read and write set overlap. If a read and write set or overlap, T1 and T2 are conflicting. And then what we have is that half of the transaction is executed, half of this is scheduled is such that T1 is executed followed by T2, but part of it is that T2 is followed by T1. In a sense, this action of adding 6% is dependent on this action of adding 100. So this means T2 is dependent on the action of T1. And it was the case here too. T2 is dependent on the action of T1 because this 6% is added on the top of the $100 that was added by T1. In this case, again, T2 is dependent on T1 because this 6% added is dependent on that $100 that was deducted. So if you look at a dependency of this transaction, T2 is always dependent on T1. T2 is always dependent on T1. So we have a unidirectional relationship, always T2 dependent on T1. But when we look at it here, T2 depends on T1 because it adds 6% to that $100 that T1 adds it. But here, T1 is dependent on T2 because T1 deducts $100 on after the 6% that was added by B. So now for some operation, we have T1 dependent on T2. On some other operation, we have T2 dependent on T1. And that creates a conflict cycle, a dependency cycle. So there shouldn't be any cycle in our dependency. It's always that if there are actions that are conflicting, or if there are transactions that have conflicts, always must be the case that either T1 depends on T2 or T2 depends on T1. Because on the serial execution is either T1 followed by T2 or T2 followed by T1. They cannot have both ways. So there's always a one-way dependencies. So as soon as we look at a schedule and we see these bidirectional dependencies forming a cycle. So if you were to draw sort of a dependency, imagine a dependency graph is that transactions are nodes in this graph and the dependency are edges. This one will say T1 depends on T2, or I could so I could say T2 depends on T1, and then on this part it would be that T1 depends on T2. So we start forming a cycle, and this will be the indication that this is not going to be serial scheduled. This schedule will not be equivalent to either T1 followed by T2 or T2 by followed by T1. It has some side effect that is impossible to produce if things were executed serially. So this does not map to a serial schedule. Or in other words, it is not a serializable schedule. A serializable schedule is a schedule that is either serial, strictly serial, executed serially, or is in a schedule that can be mapped to some serial schedule. And so the consistency, so the isolation semantics says that to kind of really be 100% sure that something is correct, we say it's a serializable schedule. This schedule is serializable. It can be mapped to a serial schedule. This one isn't, so it's not a serializable schedule. Any question?
You mentioned the dependency graph.
Yes.
How do you usually go about kind of forming that?
So the dependency graph, you kind of, once you look at a schedule, we will talk about this in later lecture, but once you look at a schedule, we can say each transaction will be like a node in a graph, and I draw an edge, and you could just take either way. So I draw an edge from T1 to T2 if there is a dependency of T2 on T1. And I also draw an edge. For any dependency, you draw an edge. So this is you could say, you could have one definition of how do you draw an edge. If T1 or T2 relies on T1, then I draw an edge from T1 to T2. So I draw an edge from T1 to T2. Now, if T2 relies on T1, then I draw an edge from T2 to T1. So now I have one edge from T1 to T2, another edge from T2 to T1. So that could be a graph, and that's a cycle in that graph. Any other question? So another way of kind of writing down these kind of at the lower level, maybe one more lower level, is that we say what T1 is doing. T1 is reading A and writing A. Because in order to add 100 to A, you first need to read the current value of A. So you read A followed by writing A. This action is also reading A, then writing A, then reading B and writing B. And in here, to subtract $100, first I need to read B and then write B. And kind of I highlighted the conflicting action or the dependent action. This read depends on this write. This read also depends on this write. So here the dependency that T2 depended on T1, here dependency is reversed. T1 depends on the write that T2 does. And that will violate being a serial schedule, because it cannot be the case that T1 is before T2, but also T2 is before T1. So we will get a contradiction. And that's why this is not a serializable schedule, because it doesn't map to any serial. There's no possible serial schedule in which T1 is before T2 and also T2 is before T1. So that's not feasible. Any question? Yes.
So how do you make sure that that's not happening? Because the interleaving is managed by the operating system, right?
Yeah, so we're going to talk about that. So that's coming up. That precise question coming up. So one more time, a bit of those definition. Serial scheduled that doesn't interleave the actions of different transactions. So it's just a strictly serial. Equivalent scheduled for any database. If I have two schedules and the net effects are the same, then I can say they're equivalent. Now, if there isn't a schedule that does involve interleaving, but that schedule is equivalent to some serial execution, then I say this is a serializable schedule. And the goal of concurrent execution is to create serializable schedule. Any single-threaded execution will always produce serial schedule, trivially. But if I'm doing concurrent execution, then in order to assess the correctness, as long as I can say that this is a serializable schedule, then I can be sure about the correctness. Of course, the question that was just asked, which is essential, is that, well, great, I know serial schedule is good, and I understand the concept of serializable schedule, but how do I actually do it? Because so far we haven't talked about how to actually do it. We simply said if we're given a schedule, we can reason about it, whether this is a correct or not correct, whether this is serializable or not serializable. We haven't talked about how do we now produce a schedule that is serializable. Of course, we could think of a way of we just go ahead and execute transaction for 10 minutes. And then after 10 minutes, well, we say, okay, what did we do? Did what we did serializable? If yes, okay, all those transactions are good to go. Well, after 10 minutes or after 1 minute, whatever we did, if it's not serializable, well, then nothing will go through. Let's redo things. So of course you can always do that. And actually some protocol does precisely what I said, but there are other ways of doing that, and in different workload and different environment, each will have its own benefit. So before actually talking about one algorithm that does that, any other questions? And in fact, the other thing is that in the transaction processing on modern hardware, so one of the book on the course website, that covers pretty much in the last 20, 30 years, all the different protocol and algorithm that researchers and practitioners in industry have come up with in order to create a serializable schedule. And that's called concurrency protocol. So the different concurrency protocol that if you apply, then you will always guaranteed to get a serializable schedule, or in a schedule that is almost serializable. It has some correctness guarantee, but it's not as strong guarantee as what serializable provides. As long as you can formalize that correctness criteria or that isolation. So the isolation doesn't have to be strictly serializable. There are weaker isolation as well too, that the database can try to achieve. And I mean, the notion if each transaction individually is sort of can preserve consistency and the constraint, well, then the serializable schedule will also preserve consistency. So that's kind of like a sort of a trivial rule. So now the anomalies. So again, the example that I provide, it was really about anomalies, is that the interference and the conflict of executing things concurrently. So one of those formulation of those anomalies, which is called reading uncommitted data, or read-write conflict, or reading dirty data, the data that has been changed. If you remember, in the buffer pool, we also use the notion of dirty, meaning once a page in a buffer pool gets modified, it's considered dirty and needs to be written back to disk once the page is evicted from the buffer pool. So now uncommitted data. So why is this bad? Is transaction 1 reads A and then writes A. Transaction 2 reads A, also writes A, and then it commits. C means commits. Now transaction T1 continues its execution. It now reads B and writes B. But at this point, for some reason, maybe constraint or for whatever reason, it decides to abort, or it gets aborted. So what is the issue here? Why is this undesired?
Because the second transaction is reading something which isn't valid anymore.
Exactly, it's reading something which is not valid anymore, or even it's reading something that never really existed, because as far as the data concerned, this vanishes forever. There's no such a thing as the value that was returned by T1, because that transaction was never committed. The data becomes goes into the version history, becomes a valid version of the data, or the valid edits of the data if those transaction was committed. If the transaction was aborted, that's saying aborted means forget about what I wrote, ignore it. But this transaction read what was meant to be ignored and act upon it and produce something else. For example, maybe this was that $50,000 was added to the account of A, and transaction 2 took that $50,000, bought a new car, but that $50,000 that was transferred to A It's not saying, okay, that money is not available, we can't give you that $50,000. But you just bought a car for $50,000. And of course, that's a side effect that we would like to avoid. And so we could make sure the isolation semantics is such that it avoids reading uncommitted data. And reading uncommitted data is not always bad. It doesn't mean that absolutely every time we have to avoid reading uncommitted data. For example, if a user is kind of an example, not exactly precise, but if the user is kind of liking a post and they have a choice of finalizing their like or not finalizing their like, and they can revoke their like. And if I have some analytics running and trying to count the number of likes, even if it counts that like that the user later revokes, it's not the end of the world. Sure, I mean, we miscount the like by 1. It's not going to affect, it's not going to have any effect. It doesn't matter. It's unimportant. But if I had transferred $50,000 and somebody bought a car with that money and I said, oops, I made a mistake, I need to reverse that $50,000, well, that's a problem. Some cases is not a problem. So it's okay to, in order to improve the performance, sometimes I wanted to be able to allow these anomalies. I don't always need the strict isolation. So sometimes it's absolutely needed to have that strict isolation. Sometimes it's okay. And almost valid data or almost accurate data is sufficient, especially when I'm doing analysis. So that's why it's important to formalize these different level of isolation and then allow the application choose the level of strictness that they want to be able to, or they can tolerate. Some application may go to tolerate low isolation semantic or weaker isolation semantic. Some application, no, absolutely needs to be a very strong isolation semantic. For example, anything with banking. You don't want to kind of give away the money or buy something with the money that you don't have. So there it's important. So that's one anomalies. Another anomalies is unrepeatable read-write conflict. So what's the issue here in this example?
The first transaction's not, they don't have the most up-to-date information.
So interestingly, you're kind of on the right point, but interestingly, the outcome of this transaction is actually correct because I read something and I read it again. I could have potentially ignored that read, and essentially this would be T2 followed by T1. However, I could also have stronger guarantee in my transaction saying that if I read something and if I read that information again, it has to be the identical information. Of course, I could have said if I read something and I read it again and that's changed, well, I can kind of compensate for that change. I could sort of figure something out and kind of discard my old reading and just take the new reading. And I can still succeed. But I could also have a much stronger, and this, I mean, sometimes that's possible, sometimes it's not possible, especially if you have read something and you've written something and now you read it and something goes back. Going back and fixing what you've already done is non-trivial. And the question is, you want to kind of simplify the application and you want to push all the burden into the database. So then it's important to have the unrepeatable read guaranteed, is that if a transaction read something and if it ever reads that again, then it must be the case that it's always read the same thing. And that's the unrepeatability. And even if, for example, we had violated, we could have potentially violated our repeatability here. So if the transaction T1, for example, had read A again, for whatever reason, since T2 has already changed A, then the repeatability would have been violated. So one of these anomalies of concurrent execution is uncommitted read, uncommitted reading of data or dirty reads, or unrepeatable reads. Another one is write-write conflict, overwriting uncommitted data, or in other words, lost updates. So what is it happening here? So first of all, transaction T1 is writing to A, and then T2 writes A, and then writes B, and it commits, which is okay so far. But then T2 also now writes what T1 had written. So it overwrites what T1 had written, and then it commits. So what happens, this write, it actually gets lost. This write will never make it. This write gets lost by that, by this commit. Or kind of looking at some of the earlier way of thinking about it, in this case, T2 is dependent on T1 because this write is dependent on this write. But all of a sudden, we're switching, now becoming T1 dependent on T2. So again, we're forming that cycle. So write-write conflict. And so that's a conflict. Things could have been even worse if this C, since it's here, at least these updates were written and it could be recorded. So maybe one can say, okay, it's not 100% lost. At least there's some track of it. But then this one overwrites it as a new version, but then it violates the semantics of the ordering, is that T1 followed by T2 and then T2 followed by T1. But if C has kind of was down here, if this later was committed, this change by this transaction will never even make it as a valid version. So there is really the update was lost. So it would have been even a bigger problem. But again, that's just another form of conflict. So this one is a write-write conflict. So we looked at here was write-read conflict. One is written and then is written and then is later read. So write-read conflict. This one is read-write conflict. Something that was read later was overwritten, and then write-write conflict. And so those are three possible ones. Those are the combination. There's no read-read conflict because if I'm just reading and somebody else is reading, well, there's no conflict because we're not changing the data. So conflict occurs as long as one of those operations is right. So the four possibility, only three of them actually results in conflict. Any question?
And these are the only anomalies, right?
There are other anomalies. These are, I would say, these are the main ones. It gets depending on the scenarios. We talk about snapshot isolation. So there are anomalies in those cases, but those are kind of outside the scope. If you look at the book, the transaction processing book that I mentioned, especially in the second chapter, we covered those other anomalies there as well too. So now coming back to that question that was asked earlier. So I know what the I know what the schedule is. I know the interleaving schedule. I can kind of reason about it, whether it's good or bad. But how do I get a serializable schedule? How do I ensure that these anomalies, for example, don't happen? One way is pessimistic. So any action I do, I make sure that I eliminate anomalies before it happens. So that's pessimistic. There's also an optimistic view of this, is that I may allow things to happen, then I kind of try to verify and validate to make sure no anomaly did occur. And if no anomaly occurred, then I can sort of allow things to commit. So pessimistic is to avoid anomalies to happen in the first place. Optimistic is to execute and then validate and verify that there's no anomalies. And if that is true, then allow commit. So we're going to look at pessimistic. We're also going to look at some optimistic approaches in the coming lecture as well too. So one classical basic approach, which is very powerful, is called strict two-phase locking, or just two-phase locking in general. And all it says, very basically, it says any transaction that needs to access the data, it needs to acquire a lock. So make sure you have, and if you're reading something, you acquire a shared lock. If you need to write something, you acquire an exclusive lock or a write lock. And if I'm having a shared lock on an object or a read lock on an object, then on a record, then any other transaction who also wants to read, they can also acquire a shared lock because there's no conflict between two shared locks. Two people can read it because there's no side effect of a read. But if I'm holding a write lock and someone wants to read that record, then they need to wait till I release the lock. Basic concept, basic read and write concept. If I'm reading something, I do a read lock or a shared lock. If I'm writing something, I do a write lock or exclusive lock. I mean, those terms are used interchangeably: read, shared, write, exclusive. And the basic idea of strict two-phase locking is that I just simply acquire locks as I need it. I get read, write, lock. But the caveat is that only when I either abort or commit my transaction, only at that point I release my lock. In other words, for the entire duration of my execution, I will always hold the lock. And why is that important? Is that if I hold the lock on a write and I hold it all the way to the end, no other transaction can read or write this. So by holding that write lock, I avoid all write-write, read-write conflict. If I need to read something, and if I lock it, then I'm going to avoid all the read-write conflict. I'm not going to allow anyone to write to something that I am reading right now. So it's not going to have a repeatability read issues. So that read-write conflict is eliminated. So, and if I'm holding those locks till the end, then then once I've hold the locks, before I access the data, once I make sure that data is protected and it's for me, then if I hold it till the end, well, all the data that I needed it is protected till the end. So that means the isolation is guaranteed. So anything that I wanted it, I essentially, the lock gives me sort of not the illusion, but it gives you the perception or the same behavior as if I was the only one that's running, because anything that I wanted to access, I'm saying I'm the only one who can access it. So essentially, it creates isolation. There is a variant of a 2PL, is that we call a non-strict 2PL, is that I can release locks, but once I start releasing locks, I cannot acquire any more locks. And the key idea of the 2PL or two-phase locking is that there is a growing phase and then there is a shrinking phase. In a growing phase, there's a phase that I can only acquire locks, but the moment I drop a lock, I can no longer acquire new locks. So I go to the acquiring phase and then the releasing phase. And as long as it ensures that I don't violate the acquiring and the releasing, meaning once I release and then I try to acquire another lock, as long as I avoid doing that, then it can be shown that the schedule is serializable. So that's the theory behind the 2PL and ensuring that it always produces a serializable schedule basic property, as long as I ensure that I don't release any locks. I don't release and require. As long as that behavior is eliminated, then it can always show that serializable schedule is produced. Now the question is, what's the what would be the disadvantage of, or what is the advantage of releasing lock early? Can you think of an advantage of releasing lock early and don't necessarily wait till the end of the transaction? What would be an advantage of that?
Maybe if a transaction reads data that a lot of other transactions are reading as well, like it's a really hot record.
Mm-hmm. Yeah, so then I kind of allow others to read. So I'm not going to block them, because as long as I hold the lock, I block them. So that's the advantage. But what could be a potential disadvantage? What if I had a write request, I had a write lock, I write something, and then I'm going to release it, but then I abort. So now any transaction who have read the data that I have written and I aborted, they also need to be aborted. So they could cause cascading abort, which complicates handling abort, and it complicates recovery and so forth. So oftentimes the strict two-phase locking is what's implemented, and two-phase locking is basically standard protocol that major database vendors have worked on it for years to get a really highly optimized implementation. So probably millions and millions of dollars have been invested to create highly efficient two-phase locking or 2PL implementation of database. I mean, this is simple, but it's something that it's almost every major vendor provides. That's all we can think of as, in a sense, a standard way of doing transaction. And again, exclusive lock, as we said, if somebody holds exclusive lock, no other transaction can either request a shared or an exclusion. So strict 2PL allows only serializable scheduled as desired. It also simplifies transaction aborts because it avoids that's what it's called the cascading aborts. Because if I release a lock early on, somebody reads it. If I abort, then any transaction that read from what I wrote also needs to abort. So 2PL does allow serializable scheduled, but it involves complicated abort processing. So it's not that trivial how to abort and how to recover. So now aborting a transaction, if a transaction is aborted, then all of its action, as we talked about, needs to be undone. And any transaction that read from them also needs to be aborted. So that's the notion of cascading abort. And basic thing is that you avoid cascading aborts by holding your locks or releasing your lock at the commit time. First transaction commits, is finalized, and once it's committed, then starts releasing the locks. Any question on that? On the cascading abort or on the 2PL? And as we talked about earlier, is that concurrency ensures the interleaving of operations, creates serializable schedule. So that's what concurrency control does. But still, I could have crashes. And so this is another part of the concurrency or the database or transaction management of the database is we have that scratchbook, we have that journal, we have that log, that any action that needs to be, any action that was done is written in there. So if a transaction later aborts and I restart, then I can go back to my log and undo any action that the transaction has done, especially if those transactions were aborted. So that's a basic notion of log. And then the log, typically, sort of a general log, this is what is being recorded. TI writes an object, the old value and the new value. In LStore, for example, as we kind of started the class with, the old value or the base value of the record is always written. And after that, only new records are written. So the tail pages essentially have this property. The new values is always written and the old values are always preserved. Log record must be written to disk before changing the page. So that means before I go and change my buffer pool page, I need to make sure that that log record is written. So I have a log record written before I go ahead and dirty a page in buffer pool. So that's one thing. And also the other thing that gets written is that whether the transaction commits or an abort. So there is a log entry of any changes of the data made by transaction. There's also a log entry for when the transaction commits an abort. If a crash happens and a transaction does not have a commit or abort entry, by default, we say that the transaction was aborted because it never reached the commit state, so it was never committed. And then these log records of the same transaction are kind of chained together. Again, this is something that we exactly do in LStore too, is that the tail pages are linked. So essentially those, you can think of the tail record as log records and they're also linked. And why they're chained and linked together, because we can find the earlier version and sort of the effect of those transactions. Of course, the tail records spans different transactions. The same transaction could do multiple writes, create multiple tail read, but also the different transaction over time for the same record creates a tail record, and all of those are also linked. Well, that's something that usually does not appear in the log. The chaining is also only limited to the actions within the same transaction. And also the log is also, and the one reason you want to keep a log and a reason you want to keep a log even for LStore is that what if the media fails, the storage media fails, my tail record, the disk that it's written to, it fails. So usually you want to have some redundancy. And that redundancy is that I have a log. So then you make sure that your log is on a different disk. And you also make sure that disk is probably duplexed, is that maybe it's on a RAID. You write it to 2 disks at the same time, 2 different locations even maybe. So your log can, even if the machine crashes, even the disk crashes, the media crashes, you have multiple copy of that log on different machines and more importantly on different disks. So that's why even if your data structure or your database design is such that you don't necessarily need log for recovery, for example, but just to protect media failure or disk failure, it's good to have a log. And so a log is typically kept either way. And the logged related activity, such as and all the sort of the concurrency activity, whether you lock a record or unlock a record, all of those, of course, is done by the database. The user is unaware of it. And the database, in the database community, there's also a difference between a latch and a log. In distributed system, or maybe not in distributed system, in operating system, the definition of lock and latch are usually interchangeably, but in database, they kind of use it differently. Lock is a logical at the level of a record. We lock a record or we lock a table. Latch is used for the data structure. So I lock a record, but when I wanted to kind of write to my page directory, I may latch my page directory to apply that update. So the lock is at the level of a record, is a logical level, at the record, or at the level of table. I lock my table or lock my record, but then I latch my internal data structure. I latch my page, or I latch my buffer pool. I latch my page directory. I latch my index. So that's kind of a distinction made in databases. In other area of computer science, they use lock and latch interchangeably. And then recovering from a lock. So there is a technique that was created, proposed by Mohammad at IBM Research in the 80s, and sort of at its culmination in 1990 or 1992, which called as the Aries Protocol. It's known as write-ahead logging. And the write-ahead logging, it's so before Mohan described Aries Protocol, believe it or not, most recovery protocols were not proven or guaranteed to always be able to recover. There was always these corner cases, and in fact, data could have been lost, and then you actually need people to sit down and manually try to recover the data. But he developed this write-ahead logging, which is called the Aries array of protocol, which provably shows that the recovery is done automatically and it's correct. And it's super simple as well too, and that's one of its elegance. So, and of course, actually, so another side note, when I was working at IBM Research, so Mohan was my mentor as well too, and he was in a lot of conversation and discussion of LSTOR over the span of number of years that I worked on this project. Is also, of course, acknowledged in the LSTOR paper too at the end. So there are three main phases of Aries protocol. One is the analysis. So once something crashes, the database crashes, and you come back on, you first do an analysis, meaning you scan the log from the last checkpoint. And the checkpoint is the point that you know that the database has already, or the disk have already reflected every change. So checkpoint is a point in time that you know your disk is up to date. Any transaction up to that point have been successfully applied to disk. So you start from your last checkpoint and you start looking at the log. And you do this to identify all the pages, all the dirty pages in your buffer pool, and you identify, so that's you identify what was changed basically. And then what you do, you identify all the changes, all the things that need to be changed, and all the pages on your disk or your buffer pool that was changed since the last checkpoint. Then you do a redo phase. So you blindly go ahead and you redo all those changes from the last checkpoint. Even if those changes already reflected on this, you don't care. You go from checkpoint and you redo every single change that was logged. Then there's a final phase, you do undo. So now you go from the end of the log and you go backward, and any transaction that was supposed to be aborted, you undo it in a backward. So analysis, identify what was changed, redo, just basically redo all the changes that was done, and then an undo. Any transaction that was aborted, you undo its change. The analysis is a forward read of the log. The redo is a forward application of the log, and the undo is the backward application of the log. Because redo, you do a forward because you need to do things in order. Undo, you want to kind of individually remove the action of the transaction in the opposite direction. And also it has some important element of this forward and backward becomes rather technical, is that the simple idea of doing things forward and then doing things backward, it allows the system to sustain or handle when crashes happen during the crashes. So if the recovery starts and you start trying to recover the database, and in the middle of the recovery, things crashes again and repeatedly keeps crashing itself, if you don't do this carefully, then we will never ever make progress. We will always stall. It would not be the case that at least after every crash, an incremental work is done. So eventually, if there's enough time between crashes, the entire database will be recovered. If you don't do this carefully, you will always get stuck. You never make any progress. So that's so I think we kind of over time, but so kind of maybe it's good to just finish this lecture, and it's going to be available offline for viewing for anybody to see them after the lecture. Okay, and that's it. So concurrent execution, and talk about the correctness of that, what it means to have a serializable schedule, and the interleaving of them, avoiding anomalies, and then finally having a log. And these are the topics that we will going to spend pretty much in the remainder of this month to really go in more and more in depth. And for the third milestone, we're really going to focus on developing a transactional system with concurrency protocol and all the interesting aspect of it. So any question? All right. Thank you so much, everybody. Have a wonderful day, and see you guys on Thursday. Thank you.